Good morning, students. Today we are going to start our new chapter, chapter 13, that is magnetic effect of electric current. And this chapter is very important as well as it is very interesting, because the thing which we are going to study in this chapter, all these things you have to face in class 12th. That's why this chapter is very important and you have to pay extra attention to understand the concept of this chapter. So without wasting time, today what all things we are going to cover. I'll give a small introduction of the chapter. Then after that we'll cover magnetic field and field lines. And after that, magnetic field due to a current carrying conductor. Now this current carrying conductor may be a straight conductor, it may be a circular loop, or it may be a solenoid. So these are the points which we are going to cover today. Now we'll come to the introductory part of the chapter. Now very basic concept of this chapter is, it was first accidentally noticed by Ørsted. He is one scientist of 19th century. What he accidentally noticed that whenever he bought a compass close to a current carrying conductor, and the compass will start showing a deflection. How it can be possible? Because this current carrying conductor produces a magnetic field, and whenever we'll bring any other magnet, the needle of this compass is made up of magnet. So whenever we'll bring one magnet in the magnetic field of any other material, then it will show a deflection. So this is the basic concept of the chapter, that whenever we will bring a magnetic compass close to a current carrying conductor, and the current carrying conductor produces a magnetic field, and this is what known as a magnetic effect of electric current. Once again, what is magnetic effect of electric current is, whenever a current is flowing through any conductor, it produces a magnetic field around it. So if we will bring any other magnetic substance close to it, then this compass will start showing us a deflection, which proves that there is a magnetic field around a current carrying conductor. So this is the basic concept of the chapter. Now I have used one term, magnetic field. Now what does that mean? Magnetic field hota kya hai? So magnetic field is the region around which, it is the region around a magnetic around a bar magnet, in which if we will bring any other bar magnet, it will experience a force. So what we can say about the magnetic field? Magnetic field is the region around a bar magnet. Suppose this is a region around a bar magnet, and if we will bring any other magnet in this region, then another magnet will experience a force because of this magnet, and that force is known as magnetic force, and the region around this bar magnet is known as the magnetic field of this magnet. So what is magnetic field? It is the region surrounding a magnet within which a magnetic force is experienced, is called magnetic field. So it is denoted by B, capital B. It is a vector quantity, so we can mention a vector over it. So it is a vector quantity. If it is a vector quantity, that means it do have both the direction as well as the magnitude, and we can measure the magnetic field in Tesla. Tesla is the SI unit of magnetic field, after the name Nicholas Tesla. Now next is magnetic field lines. This is also very important point. Magnetic field lines are the imaginary line. They are the imaginary lines drawn around a magnet which shows the direction of magnetic field. मतलब ये सारी rays हैं, these are the imaginary lines drawn around a bar magnet which shows the direction of magnetic field at any of the point. So this is all about the magnetic field lines. Now there are some properties of these are the magnetic field lines. There are some properties of the magnetic field lines which are very important to understand. Now first property, we have to keep this diagram. So first is, they travel from north pole to south pole outside the magnet, and south pole to north pole inside the magnet. Suppose this is our magnet. The magnetic field lines are coming out from the north pole and they are moving towards the south pole. Outside the magnet they are moving from north to south, but inside the magnet they are moving from south to north. So this is first property. Second property is, they are closed and continuous curve. यहाँ से स्टार्ट होंगे तो ये यहीं पर खत्म होंगे, which means they are forming a closed and continuous curve. Third point, they are denser near a pole. They are denser near the pole and becomes rarer as we move away from the pole. अगर हम बार मैग्नेट के पास में हैं तो यहाँ पर ये सबसे ज़्यादा डेंस होते हैं, और इससे दूर जाएंगे तो then it will become rarer. Next point is, Denser line represent a strong magnetic field. We know that कि whenever we are moving towards the pole, यहाँ पर सबसे ज़्यादा magnetic field होती है और यहाँ पर सबसे ज़्यादा magnetic force experience कर सकते हैं हम. So wherever the magnetic field lines are denser, there the magnetic field strength will be greater. And as we move away from the magnet, the magnetic field lines will become rarer and the magnetic field strength will get reduced. Now one very important point is they never intersect each other. Magnetic field lines never intersect each other, because if they do so, अगर ऐसा होता है मैग्नेटिक फील्ड लाइंस अगर किसी पॉइंट पे इंटरसेक्ट करती हैं तो उस पॉइंट पर मैग्नेटिक फील्ड की दो डायरेक्शन हो जाएंगी. फॉर एग्जांपल अगर यहाँ पर इस पॉइंट पर हमें मैग्नेटिक फील्ड की डायरेक्शन देखना है, देन विल ड्रॉ अ टेंजेंट एट दिस पॉइंट. एंड अगर यहाँ से एक और मैग्नेटिक फील्ड आती है ऐसी, तो यहाँ पर एक इसकी दूसरे वाले मैग्नेटिक फील्ड की डायरेक्शन क्या हो जाएगी, ये हो जाएगी. सो एट द सेम पॉइंट देयर विल बी टू डायरेक्शन ऑफ मैग्नेटिक फील्ड, एंड विच इज नॉट पॉसिबल. इट इज इम्पॉसिबल टू हैव टू डायरेक्शन ऑफ अ मैग्नेटिक फील्ड एट अ सिंगल पॉइंट. दिस क्वेश्चन इज वेरी इंपॉर्टेंट, दैट व्हाई डू मैग्नेटिक फील्ड लाइन्स नेवर इंटरसेक्ट ईच अदर. सो द आंसर विल बी मैग्नेटिक फील्ड लाइन्स विल नेवर इंटरसेक्ट ईच अदर, बिकॉज if they do so, there would be two direction for the same magnetic field, which is not possible. So this is very important point of out of the properties of magnetic field lines. Now next is uniform. One important point is uniform magnetic field. What is uniform magnetic field? If the magnetic field lines are parallel and equidistant, then the field is said to be a uniform magnetic field. Now look at the diagram. Here all the magnetic field inside the bar magnet are parallel, and hence we can say that the magnetic field inside the bar magnet is uniform magnetic field. But when we move away out of the bar magnet, there is somewhere it is very denser magnetic field lines, somewhere it is rarer. So we cannot say that the magnetic field lines are uniform. But inside the magnet we can say that the magnetic field lines are uniform magnetic field inside a solenoid. So there is one activity given in your book in which a bar magnet is placed over a cardboard, and there are some iron flings spreaded over it, and when we will tap the cardboard, the iron flings will automatically organize themselves in a regular pattern, and this pattern will show us the direction of the magnetic field or the pattern of the magnetic field around a bar magnet. On the basis of this we have drawn this diagram. So this is very important, that the magnetic field lines do have this type of pattern, that they are always moving from north to south, and they will never intersect each other, and the magnetic field are very strong near the pole, and as we move away from the pole they will become weaker. So these are the very important points about the magnetic field. Now next point which we are going to cover today, magnetic field due to a current carrying conductor. Now first of all, if the current carrying conductor is a straight current carrying conductor, then what will be the pattern of the magnetic field around the straight current carrying conductor? This we have to understand. Suppose this is a cardboard and this red color is a conductor, and this conductor is passing through the cardboard, and it will spread iron flings around it. Then the iron flings will automatically organize themselves in a circular form, or we can say that the direction of magnetic field will be in a concentric form. So how we can say that? Because the iron flings organize themselves in a concentric circles, and this pattern will be the direction of magnetic field around a straight current carrying conductor. So on the basis of this, what we can say that the magnetic field is represented by concentric circles, which becomes larger and larger as the distance increase from the current carrying conductor. As we'll move away from the current carrying conductor, the radius of the concentric circle will get increase, and as we move away from the current carrying conductor, the magnetic field strength will reduce. So how we can say that? Magnetic field become weak as the distance increases from conductor, or we can say that B is inversely proportional to the R, where R is the distance from the current carrying conductor. And one important note is there, magnetic field increases on increasing the current in a conductor. If we'll increase the amount of current flowing through the conductor, automatically the magnetic field around this conductor will get increased. So we can conclude with 2 points that magnetic field is inversely proportional to the distance, and magnetic field is directly proportional to the current passing through the conductor, and the pattern of the magnetic field around a current carrying conductor is in the form of concentric circles. Now if we want to know the direction of magnetic field, then how we can do that? So we apply a rule called right hand thumb rule. This rule is also very important, and it is also known as Maxwell corkscrew rule. So if we want to know the direction of magnetic field around a current carrying conductor, then what we'll do, suppose this is a current carrying conductor, and the direction of the current is moving from this point to this point, and we'll hold this conductor like this. Okay, so the direction of the current will be represented by the thumb, and the curls of our finger will show us the direction of magnetic field like this way. This is the direction of current, and the curls of our finger will show us the direction of magnetic field. So this is the rule given by Maxwell corkscrew. This is also known as the Maxwell corkscrew rule. This is the diagram of the rule, in which the thumb will show the direction of current, and the curls of our finger will show the direction of magnetic field. This is very important rule in order to know the direction of magnetic field around a straight current carrying conductor. Okay. Now this is also known as Maxwell corkscrew rule. Now the third point is current through circular loop. Now in the previous point, we have covered that how the magnetic field lines will be represented around a straight current carrying wire. Now if the conductor is drawn into the loop, अगर उसको हमने एक loop में convert कर दिया, then how we can know the direction of magnetic field? Now first of all we will cover some point. Circular and concentric field. This is the diagram of a circular loop in which the direction of current is moving from here and it is coming out from here. So this is the diagram. Now the direction of magnetic field we have to find. First of all, circular and concentric field near the coil. If we'll move close to the coil, it will be a circular loops will be formed of the magnetic field. Now near the central field, this is the near central field, are straight and parallel. These are the parallel rays. यहाँ से ये ऊपर की तरफ जाएंगे. At the center field is perpendicular to the plane of the coil. At the center of the loop, the direction of the magnetic field will be a perpendicular to the plane of the coil. Now इसको थोड़ा यहाँ पे समझने में थोड़ा सा प्रॉब्लम होता है, तो हम इसको फ्रंट व्यू लेते हैं, इसका फ्रंट व्यू कंसीडर करते हैं. दिस इज द फ्रंट व्यू. नाउ व्हाट विल बी द डायरेक्शन ऑफ करंट? सपोज इस पॉइंट पे हमें इसको पकड़ना है. ये कॉइल है, इसमें करंट की डायरेक्शन ये रही. अब और यहाँ पर करंट की डायरेक्शन इस टाइप, मतलब ये एंटी क्लॉकवाइज डायरेक्शन में करंट मूव कर रहा है. नाउ व्हाट वी विल डू, वी विल होल्ड दिस, इसके अंदर से हाथ लेके जाएंगे और ऐसा रखेंगे, एंड द थंब विल शो द डायरेक्शन ऑफ करंट. तो इसके बेसिस पे क्या होगा, यहाँ से मैग्नेटिक फील्ड अंदर से ऊपर की तरफ आएगी. और सेम चीज़ यहाँ पर करेंगे, तो इधर से भी हम राइट हैंड को इधर से नीचे से पकड़ेंगे ऊपर की तरफ, तो थंब विल शो द डायरेक्शन ऑफ करंट, और मैग्नेटिक फील्ड इसके अंदर से ऊपर की तरफ निकल कर आएगी. सो द डायरेक्शन ऑफ मैग्नेटिक फील्ड इन दिस कंडीशन और इन एंटी क्लॉकवाइज डायरेक्शन में क्या होगा, इट विल कम आउट ऑफ द प्लेन. तो इसमें डायरेक्शन ऑफ करंट विल बी आउट ऑफ द प्लेन, सॉरी, it will be out of the plane. But when the direction of current will be clockwise, अब clockwise direction में क्या होगा, तो इसके thumb will show the direction of current and the curls of our finger will be like this. तो इसको हम अंदर ऐसे पकड़ेंगे, इस अगर ये रिंग है तो इस रिंग को कैसे पकड़ेंगे, ऐसे पकड़ेंगे. इन दैट केस हमारी जो मैग्नेटिक फील्ड है वो ऊपर से नीचे की तरफ जा रही है, मतलब इट इज गोइंग इनसाइड द प्लेन. सो व्हेन एवर द मैग्नेटिक फील्ड लाइन इज मूविंग इनसाइड, तो इट इज रिप्रेजेंटेड बाय क्रॉस. व्हेन एवर द मैग्नेटिक फील्ड लाइन इज कमिंग आउटसाइड, देन इट इज रिप्रेजेंटेड बाय अ डॉट. सो यहाँ पे मैंने मेंशन भी किया है, मैग्नेटिक फील्ड इज कमिंग आउट ऑफ द प्लेन. यहाँ से मैग्नेटिक फील्ड बाहर आ रही है और यहाँ से मैग्नेटिक फील्ड अंदर की तरफ जा रही है. सो वी कैन नो द डायरेक्शन ऑफ मैग्नेटिक फील्ड ऑन द बेसिस ऑफ द मैक्सवेल कॉर्कस्क्रू रूल और राइट हैंड थंब रूल इन सर्कुलर लूप ऑल्सो. इस लूप को भी अगर हम किसी भी एंड पे अगर ऐसे पकड़ेंगे तो यहाँ पे डायरेक्शन ऑफ मैग्नेटिक फील्ड हमें मिल जाएगी. ओके, सो यहाँ पर भी क्या होगा, मैग्नेटिक फील्ड इज डायरेक्टली प्रोपोर्शनल टू द करंट. वट एवर बी द अमाउंट ऑफ करंट इज फ्लोइंग थ्रू अ लूप, the magnetic field is directly proportional to the current passing through the loop. Second is magnetic field is directly proportional to the number of turns in the coil. Whatever may be the number of turns in the coil, the magnetic field will increase on increasing the number of turn. क्योंकि एक बार coil complete होती है, coil का एक loop बनाते हैं, तो उसमें से कुछ amount of magnetic field होगी. ऐसे ही अगर हम n number of loop बना देंगे तो वो magnetic field n times हो जाती है single loop के. So this is all about the current through a circular loop. Now what will be the solenoid? Now पहले जो मैग्नेटिक फील्ड हमें कैलकुलेट करनी है, मैग्नेटिक फील्ड ऑफ अ करंट कैरिंग सोलेनॉइड. अगर हमारे पास कोई सोलेनॉइड है, उस सोलेनॉइड से के अंदर से मैग्नेटिक फील्ड की लाइन, मैग्नेटिक फील्ड की डायरेक्शन क्या होगी, दिस वी हैव टू फाइंड. बिफोर अंडरस्टैंडिंग दिस कंसेप्ट वी हैव टू नो द व्हाट इज सोलेनॉइड. सोलेनॉइड क्या है ये समझना पड़ेगा. तो सोलेनॉइड इज अ coil of many turns of insulated copper wire wrapped closely in a shape of cylinder is called a solenoid. जैसे कि ये बना इसका डायग्राम. ये एक इंसुलेटेड कॉपर वायर है, उसको हमने वाउंडेड कर दिया, गोल गोल घुमा दिया. इट इज़ जस्ट लाइक अ स्प्रिंग. जैसे स्प्रिंग होता है वैसे ही होता है, उसका सिलेंड्रिकल शेप होता है. सो दिस इज अ सोलेनॉइड. So whenever will pass a current through a solenoid, the magnetic field in a solenoid will exactly same as that of a bar magnet. जैसे बार मैग्नेट की मैग्नेटिक फील्ड होती है वैसे ही सोलेनॉइड की मैग्नेटिक फील्ड होती है. बट इसमें हमें करंट की डायरेक्शन के ऊपर डिपेंड करता है कि उसका नॉर्थ पोल किस तरफ होगा और साउथ पोल किस तरफ होगा. और यहाँ पर एक और चीज़ है कि मैग्नेटिक फील्ड ऑफ सोलेनॉइड इज डायरेक्टली प्रोपोर्शनल टू द नंबर ऑफ टर्न्स. जितने ज़्यादा नंबर ऑफ टर्न्स होंगे उतनी ज़्यादा मैग्नेटिक फील्ड स्ट्रांग होती है. सेकेंड पॉइंट, it is the magnetic field of a solenoid is directly proportional to the current के directly proportional होती है. If will increase the value of current, automatically the magnetic field will get increased. Now comes the polarity of the ends of solenoid is determined by using clock face rule given below. मतलब यहाँ पर देखें, अगर हमें इसमें ये बताना है कि कौन सी डायरेक्शन नॉर्थ पोल के जैसे बिहेव करेगी, कौन सा साउथ पोल के जैसे बिहेव करेगी, इन दैट केस वी हैव टू यूज अ क्लॉक फेस रूल. सो इन क्लॉक फेस रूल, सपोज हमने इसका एक एंड देखा, उस एक एंड में हमने सामने से देखा इसमें, और करंट की डायरेक्शन में ऐसी मिल रही है, तो इससे हमें क्या मिल जाएगा, ये एस बन रहा है. दैट मीन्स अगर ये क्लॉकवाइज डायरेक्शन में है, इसका मतलब वो एंड हमारा साउथ पोल होगा. और अगर दूसरा एंड हम देखते हैं और वो अगर एंटी क्लॉकवाइज डायरेक्शन में करंट है, तो वो कैसा हो जाएगा, नॉर्थ पोल. यहाँ से हमारा एन बन रहा है और यहाँ से हमारा एस बन रहा है. तो एस स्टैंड फॉर साउथ पोल एंड एन स्टैंड फॉर द नॉर्थ पोल. Now one very important note, a strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron. इसके अंदर जो मैग्नेटिक फील्ड बनती है वो बहुत स्ट्रांग होती है और यूनिफॉर्म मैग्नेटिक फील्ड होती है. तो उस यूनिफॉर्म मैग्नेटिक फील्ड को हम यूज़ कर सकते हैं इन ऑर्डर टू मेक इलेक्ट्रोमैग्नेट्स. If we'll place a soft iron inside this solenoid, then there will be a situation in which the soft iron will be magnetized, and that substance, that soft iron can be considered as a electromagnet. So this is very important, and you have to understand the concept of this. Thank you.